There has been much discussion about sending manned missions to Mars. Surviving on the surface of the red planet will present difficult, but not insurmountable challenges. One problem is the exposure to radiation on the surface. The astronauts who landed on the moon were exposed to this as well, but they were only on the moon for a few days, while a Mars mission would likely last months. The suits and habitat modules would require radiation shielding, and even then, astronauts would likely have to bring supplements to mitigate the effects of radiation sickness, such as iodine. The perchlorates in the soil present a serious chemical health hazard. When explorers exit and enter the habitat modules, they will inevitably bring perchlorates in through the airlock, and this will cause damage to their respiratory system when inhaled. One way to mitigate the effects of these hazards would be to put the habitat modules in subsurface lava tubes. These would provide natural radiation shielding and could mitigate the worst effects of the perchlorates, since the astronauts could use an air hose to remove most of the perchlorates near the entrance of the lava tubes. One problem that might come about from spending a long amount of time on Mars is the impact of low gravity. When astronauts spend long periods of time in zero gravity, some of the deleterious impacts include loss of bone, weakening of the muscles, decreased volume of blood plasma, and difficulty in maintaining posture. The impacts of low gravity are yet to be quantified. It may be that a person would start to suffer from deleterious effects on Venus with 90% Earth's gravity after a few months, or humans might be fine on Mars with 34% Earth's gravity indefinitely. We just don't know. Traveling to Mars would pose similar problems such as radiation, but the travel time is short enough that the astronauts can be put into an artificial comatose state and reside in a radiation-shielded container, so that the entire craft doesn't have to be shielded, which saves a lot of mass. When visiting another planet which may or may not harbor a biosphere, preventing contamination by earthly organisms is a high priority. Modern treaties pertaining to space travel stipulate that any probe sent to another planet has to be sterilized. Modern probes are usually heat sterilized by heating their surfaces to 114 degrees Celsius. However, probes have been sent to Mars before this treaty was signed. These certainly carry dormant bacterial spores to Mars, but could they have effectively contaminated the surface? Although many bacteria that we encounter on a day-to-day basis can form spores which can survive in the vacuum of space and survive for over 100,000 years, this doesn't mean that they can also metabolize and reproduce once they get to Mars. Even during the best of times on Mars, the hardiest microorganisms on Earth would have difficulty surviving. Furthermore, these extremophiles usually live in remote, desolate environments, so it's extremely unlikely that any organism found in a space launch facility could grow and metabolize on Mars. Conversely, many astrobiologists have argued that life on Mars could be harmful to Terran life. This is largely because any Martian surface microorganism would live in an environment where organic carbon is so rare that it would immediately start breaking down any source of it, and thus quickly infect humans. This is unlikely, given how natural selection impacts reproduction rates. There is usually a trade-off between being able to metabolize and use a substance at very low concentrations and the maximum rate at which it can be used. The lower the minimum concentration of a metabolite which can sustain cellular growth, the lower the maximum rate at which the organism can use it, no matter how abundant the metabolite is. Similarly, any Martian microorganism would be able to consume organic carbon at an extremely low rate, no matter how much of it there was. Furthermore, Terran life would likely have very different biochemistry to Martian life, making it difficult for one to consume the other. Once humans have landed on Mars, they will have to eat. Bringing food will incur a large mass penalty on any craft headed for Mars. Instead, astronauts conducting multi-year missions might grow their own food. When perchlorate salts were cleaned from simulated Martian soils, plants could grow in them. However, they are grown in Earth's atmosphere, and the major differences here are the abundance of nitrogen in the atmosphere and the higher ambient pressure. Many plants have symbiotic relationships with diazotrophic bacteria in their roots, which convert molecular nitrogen into ammonia, which plants can then bind to organic molecules to produce amino acids. Furthermore, if the pressure is lower, the ambient temperature will be closer to the boiling point of water. This will increase evapotranspiration, resulting in dehydration. With nitrogen, a minor constituent of the Martian atmosphere, plants grown in a greenhouse on Mars would have to be provided with nitrogen. This can come from human waste, which would also give the plants essential elements such as potassium and phosphorus. Since much of Mars has an atmospheric pressure too low to support liquid water, any plants grown on Mars would have to be housed in a pressurized chamber. However, as long as the temperature is kept below 25 degrees, the pressure would have to be kept at 3,650 pascals, 6 times the pressure of most of the Martian surface, while any habitat module would have to be kept at over 20,000 pascals. This means that the farming module of a Mars base wouldn't need to be as structurally sound as the habitat module and could contain a larger volume relative to its total mass. Evapotranspiration can still be a problem in a low-pressure environment, but in an enclosed space, the air will quickly become saturated with water vapor, which would curtail evapotranspiration. This might require quite a bit of water, but the demand could easily be met if the base was built by a glacier. Finally, if sunlight was used, the windows would have to absorb UV light to protect the plants. But can we manipulate the Martian environment at a much greater scale? After we first visit Mars, it is speculated that we will try to turn it into a second home. We'd supposedly do this by terraforming or making a given planet more Earth-like. The first step would be to make the atmosphere breathable. Although molecular oxygen is a trace component of the Martian atmosphere, oxygen is the second most abundant element in the Martian crust. As such, oxygen can be baked out of rocks and released into the air. However, the elemental material for other major constituents of Earth's atmosphere, most notably nitrogen, are quite rare on Mars and are thus unlikely to be a major component of a future terraformed Martian atmosphere. Since Mars is nominally very cold, the planet will have to be warmed to make it more habitable. This can be done by adding greenhouse gases to the atmosphere. We usually think of carbon dioxide as a greenhouse gas, but if there is enough carbon dioxide to induce a sufficient greenhouse effect, it would likely have deleterious effects to human health. Instead, methane and nitrous oxide can be used to warm the planet. Nitrous oxide can be produced from nitrate ores on Mars, which, while not enough to make an atmosphere as thick as Earth's, would be sufficient to induce a greenhouse effect. All this suggests that a terraformed Martian atmosphere would have an atmospheric pressure about 1/4 that of Earth at sea level, which would be roughly 95% oxygen, with carbon dioxide, water vapor, methane, argon, and nitrous oxide being minor components. With little molecular nitrogen available, plants on a terraformed Mars will either have to be actively fertilized or have microbial symbionts which can take up nitrogen as nitrous oxide. There is some water on Mars today, but it's nowhere near the quantity present on Earth. Furthermore, at an elemental level, hydrogen is rare, so there wouldn't be much of it to react with oxygen to form water. Because of this, while lakes and rivers could exist on a terraformed Mars, oceans are unlikely. An ever-present problem will be the radiation due to the lack of a magnetosphere. So, any life sent to live on Mars would probably have to be genetically engineered to better tolerate it. In summary, if life on Mars existed, it probably began in a volcanically fueled, reducing hydrothermal environment. There are a number of potential energy sources early life on Mars could have used, including polyphosphate hydrolysis, sunlight, and the fermentation of abiogenic carbohydrates and amino acids. Later on in the Hesperian, Martian life could have colonized the deuteronilist ocean, where they evolved the ability to utilize redox chemistry induced by the increasingly oxidizing atmosphere. The early Amazonian biosphere likely resembled some of the coldest, driest, and salty environments of the modern Earth. On the surface of modern Mars, a combination of hardships such as toxicity, radiation, aridity, and oligotrophy probably renders the surface uninhabitable. However, Martian life may have found a suitable refuge deep underground. As of now, we've sent probes to Mars with manned missions in the foreseeable future. Terraforming Mars to make it Earth-like will be a challenging but not insurmountable task.